when you heard about microfluidics approach from physicists, and this time you may hear someone from electrical engineering point of view. One of the main research efforts in biodynamics community is lab on a chip. And this is a slide that I borrowed from Caliper website. And this slide shows very well, clearly, the concept of lab on a chip. And conventionally, chemists and biologists having some experimental reaction can be followed by the tech bio reaction in this wet chemical bench. And people want to try to integrate all this chemical reaction into this single substrate chip, so-called lab on a chip. By having this one, we can have a very small scale of the reaction, and from this reaction, we can have a very fast response time, and we may use very small amount of reagent, which are typically very expensive. In order to achieve this miniaturization in a single substrate, the critical research is to bring up a microfluidic component. At KAIST in our laboratory, we have been working for development of disposable microfluidic system for single-cell analysis. To have this single-cell analysis, there are many components necessary. Of course, microfluidic components, such as micromixers, pump and valves, have to be developed. And also microreactor is necessary for single-cell capturing and reagent nanoliter drug injection. And also having this drug injected, we have to detect the cell separation. So we have to develop some microdetector. And in order to have this system as a self-contained microsystem, disposable microsystem, we would like to have some of the power source into this system. So in this talk, let me briefly talk about some of the components we have to develop. Micromixer, pump, and single chip reactor with a non-rigid drug injection, and power source with pipelines. Micromixer is necessary, and a lot of people are doing research on micromixer and microfluidic systems. And mixing is necessary for biochemistry analysis, drug delivery, sequencing, or synthesis of nucleic acid. These basic components is very difficult to achieve at the microscale because the microscale in the small dimension Reynolds number is very small. And you may know Reynolds number is the dimensionless ratio of viscous force versus inertial force. Because of this low Reynolds number, flow is getting nominal flow. There's no turbulence. Therefore, it's very difficult to mix. There are a lot of research going on. One of the approaches is active mixer. This point, Professor Kwang-Seok presenting about the active mixer, doing agitated by using electromagnetic energy. And some people presented micro mixer, active mixer using ultrasonic agitation. However, if you have active mixer, it's very difficult to integrate them, and costly is very expensive. So people wanted to have a passive mixer without having any external energy source. This is a simple Byoung-Gyun micromixer. You can easily fabricate it. This is done by PDMS. And when you take a look at it, actually this Byoung-Gyun mixer flow does not mix at all. And one flow is phenolphthalein, and the other one is sodium hydroxide. Phenolphthalein is a pH indicator which will change its color into red where the pH level is higher than 7. So when this phenolphthalein solution is meeting with the sodium hydroxide, color changes into red. And this is a boundary between two flows. And these boundaries maintained up until the fourth stage, and it doesn't mix at all, except for little diffusion. This microchannel cross-section is 400 micron by 200 micron, and the flow rate is about 1 milliliter per second, and equivalent to the Reynolds number 42. So we propose a pseudo 3D passive micromixer, which was briefly shown by Dr. Listro in the previous talk. In this micromixer, we wanted to use two main mixing principles. One is lamination, the other one is tailgate action. Having that one, we have mixing these two flows and spreading up and down and beating together, and spreading again and beating together. It's very easy to fabricate this and low-cost disposable system. This one shows the lamination in pseudo-solid acid micromixer. The yellow flow is coming into the upper channel, and the violet flow is coming from the lower channel. In the first stage, it's going to be it and making a two layers and having one interface. When it moves along, it's splitting into two and moving into this channel. And finally, it's going to merge into the first section, making a 4 layer and 3 interface. As it moves along, it will change into 8 layers, 16, 32, and so forth. Therefore, at the stage, it has a lot of intersections, which will enhance diffusion and mixing. The fabrication process is very simple and standard. Using a SUA as a mold, we're putting PDMS on the top and cure it and peeling off and having 2 PDMS pieces. After having oxygen plasma treatment, we bond it together and putting some silicone tubing. This is a fabricated PDMS channel structure. Channel dimension is width is about 400 micron and depth is 200 micron. And this channel, screen channel is repeated 6 times. And we're using a screen pump for testing the mixer. This is the testing mixer. Again, here we're using a phenolphthalein solution and sodium hydroxide. And when it mixes together very well, the color will completely change into red. When you take a look at it, the first stage doesn't mix very much. The second change, the color starts changing into red. Finally, up to the 5th stage, we see that mostly the flows are mixed together. This one is the Reynolds number down to 55 or 27. We observe that by having this chaotic advection and lamination, we can have a very good mixing. This is a video clip of the mixer. Obviously, 2 solutions coming into and then changing the color into red. And the 5th stage, pretty much the color changed into red. So mixing is completed. We also testing some of the lamination effect by having fluorescent tagging. We just measured this one with the help from the Department of Biology using their group of microscope. And this is the flow coming in, and it's 2 layers. This is intersection. The second stage is spread it into 2, and the next stage is beating into 4 layers. It's not completely 4, but it's pretty much 4 layers. And we have done some CFD simulation, and experimental data and the CFD simulation show pretty good relationship. So currently, we are doing an optimization of the microflow mixer channel and some other good ideas by using this simulation tool. The other one is micropump, and we are making a mechanical lens-based micropump. This one shows the generalized schematics of the membrane-type micropump with passive check valves. Principle is quite simple. We need 2 check valves and 1 membrane diaphragm. When you're moving this membrane diaphragm, this check valve will be open. When the diaphragm moves downward, this inlet check valve will be open, and the flow is coming from inlet. When this diaphragm moves upward, this check valve will be closed, while the other one is open up. The flow will be flowing out from this chamber into the outlet. By having this micro actuator, this membrane moving back and forth, actually we are pumping the flow from inlet to outlet. The question is, what kind of actuation mechanism we can use? We are targeting for disposable microsystem. Therefore, the actuation mechanism has to be a low power as well as low voltage operator. When you take a look at the many actuation types, piezoelectric, electrostatic, thermodynamic, electromagnetic, even bimetallic and shape memory structure. Some actuation has very high voltage, like 100. For example, piezoelectric and electrostatic requires about 100 volts operation, even the power is small. However, the other actuation mechanism requires large power consumption, although the voltage is very small. So we're thinking about which kind of mechanism, actuation mechanism we have to use. Then we come up with the surface tension. And I love to show this video clip coming from movie ends. And in the micro world, surface to volume ratio is getting smaller and smaller. And surface tension is a dominant force and much higher than inertial force. Therefore, in this movie clip, having a date together, and one of them is trapped in the water body, but it never came out. And the other one is trying to help him out to get it out, but cannot, because inertial force is not enough to get out from the surface tension until this water body is broken by hitting on the ground. Therefore, surface tension is a good actuation mechanism for low power application. So we designed a micro pump to verify this surface tension. This is using a well-known microwave actuation mechanism. When the mercury or liquid metal is located in electrolyte, there is a uniform surface charge distributed. When you apply the electrical field into this electrolyte, there will be a gradient of the charge. Due to this charge gradient, there will be a different surface tension between the left-hand side and right-hand side. Due to this difference in surface tension, this mercury will move into the right-hand side. When you're swapping the electrical field, this mercury will moving backwards and back and forth. By utilizing this mechanism, you can build a micro pump. There's a mercury here inside, and it can tap in the electrode. When the mercury is moving in the right-hand side, this check valve will be open, and this check valve will be closed. Therefore, the flow is coming from inlet to this inlet chamber, and flow is coming out from this outlet chamber to the outlet. When the mercury is moving to the left-hand side, this will flick the deflection of the diaphragm reversely. Therefore, the flow is coming from left chamber into the right chamber. And with this mercury moving back and forth, we can eventually pumping the liquid from inlet to the outlet. This slide shows the video clip of this mercury moving. And these are two electrodes. And this is the mercury channel. This white one is mercury. And when we're sweeping the voltage between these two, the mercury can be moving back and forth. And an important fact is that this is very low power operation. We apply only 2.3 volts, and this is about 100 microwatt operation. And from this, you can achieve about 70 microliters per minute pumping with the 2.3 volt maximum voltage, and we had a pump consumption of 170 microwatt. And this is the pretty lowest power consumption micro pump available. Next topic is a cell analysis trend. Recently, cellular engineers have quite a passion among the community, because from this cellular engineering, we can develop a new diagnostic and therapeutic agent or biochemical mechanism by using a biological cells. Having this one, you can have a drug screening. Also, you can detect some of the toxicity of the new drug candidate by using a normal living cells. Typically and conventionally, these have been done with a large number of cells. Therefore, it is a pretty time-consuming work, and it requires a large sample volume. Very expensive. And furthermore, the drawback of conventional technology is it's just getting the information, the average response from the cell. You cannot monitor each individual single cell. Therefore, it's very required to making a system for single cell analysis. Why do we need a single cell? Because we don't want to include any interference or crosstalk between two cells. In the two cells, between cells, hormones, ions, neurotransmitters are communicating each other. So we wanted to monitor each individual single cell. In order to have this, we have three components. First one is single cell isolation. We have some cell suspension meters coming in, and we have to capture only single cell, cell by cell. So we need a single cell positioning system by using microfluidics. The second one is a drug injection. You need to inject the drug in the nanoliter scale into each individual target single cell. Finally, if there is any cell secretion, we want to detect it. So we have to build some single cell monitoring system. In this research, we use laminar flow. By using laminar flow, we put and capture a single cell in a specific position. And also having surface tension, we have a surface treatment making some portion is hydrophobic, some portion is hydrophilic. We can specifically inject the drug into a specific target point. I'll show you how we made this one. This is a proposed single cell positioning and nanoliter drug injection step. And here is the laminar flow is coming into with the cell suspension media. And this cell is moving along with this flow and captured in the cell positioning site. And this picture shows the magnified view of each individual cell positioning site. When the laminar flow is coming through here, I show you this is flow direction, pretty laminar flow. And when the cell is coming into, and this flow is designed in a way that a single cell is moving into and captured in the cell positioning site. Once the cell is captured in this positioning site, the flow into this drain channel will be smaller. Therefore, the other cell is not captured this one anymore and moving along with the other laminar flow. After having a single cell captured, we are injecting drugs from this drug injection channel. Because this is a laminar flow, this injected drug does not mix with this buffer solution. So having this one into a multiple segment, we can individually inject different drugs for individual cells. This is a fabricated cell check. We have an inlet where the cell media is introduced, and this is an outlet where the cell media is coming out. And each side cell is being captured. And there's a drug injection port as well as drug drain port. There's some electrode using the gold, because we would like to measure the electrochemical reaction of each single cell when the drug is injected. This is the experimental result for cell positioning. We are using two types of experiments. One is using just polyethylene B, which is about 15 micron. And here you see this is the positioning site, and single bead was captured in this site very well. And also we're using the real living cell, and CHO or CHO cell. This is come from Chinese hamster ovary cell, which has a size of about 12 micron. And you may see it, it's very difficult to see it, but here in capture site is one cell there, and the other capture site is the other cell. So we can successfully capture a single cell in each individual site. And after capturing this cell, we can inject a drug specifically. And actually, this one shows how it works. And here, this white region is hydrophobic region, and the rest of it is all hydrophilic. When the cell is captured in this positioning site, drug is injected from the injection inlet. And we can emulate this experiment by using bluing. So bluing can introduce, and it stops here because this white region is hydrophobic region. So with a certain limit of the pressure, this ink does not flow into the system. When you increase the pressure, actually this ink starts to flow into this hydrophobic region until it meets this liquid, which is a cell media. Once it's meeting it, it just flows here because there's always laminar flow coming through. But remember, this is a laminar flow. Therefore, this media solution and this drop or blue ink does not mix at all. Therefore, this ink is always coming out from through this drain channel. So we have a little buffer drain channel. So any overflow drop can be drained from this buffer channel. This is the video clip of this drug injection. The drug is here, and then we increase the pressure, and it moves up, and air is leaking out through here. So there's also, and then it's moving into this flow, and at this point we turn off this media, therefore it's diffusing a little bit. And we turn it on again, this laminar flow, and suddenly it's just moving down to this drain channel. So this drug does not mix with this buffer solution. Therefore, in the next stage, we can inject other drug, and this drug and the other drug doesn't mix at all. So we can specifically inject drug into a single cell. The last part is the power source. This is we haven't gone too far, and we wanted to develop some of the micro source. And actually, we designed micro combustion engine because it has higher power density ratio. However, we have some problem for scaling this micro combustion engine again because surface to volume ratio is getting higher in the smaller dimension. The energy we can achieve, we can acquire from burning the fuel is proportional to L to third power because it's a volume. However, heat loss is a conduction through the surface. The surface is a L to squared power. The scaling of the heat loss is L to second power. Therefore, there's a certain dimension where the quenching is happening. And below this dimension, the energy we acquire from burning the fuel is less than a heat loss by conduction. So it's difficult to scale this combustion engine. Actually, my one was in his presentation of plenty of room at the bottom, Feynman said that this rapid heat loss would prevent the gasoline from exploding. So an internal combustion engine is impossible in nanoscale. That is true. So we have to select the dimension as well as we have to select the material. And in this micro scale, combustion engine should have an insulating material as the engine body, which means that we cannot build the engine by using a metal. So we selected a glass. The glass has very low thermal conductivity. So actually build a micro engine using the glass substrate. And we use the photosensitive glass to kind of this structure. We have a gas inlet and it just a hole. And we have in the second layer of the glass wafer, we put a piston, we have a check valve, we have a spark plug. And we're building this spark plug using nickel plating. And finally, the bottom layer is just a supporting glass. The principle is simple and well known. This is a two-cylinder combustion engine, just like a motorcycle engine. And there's two chambers, and one chamber is forwarding. The piston is moving in the other direction, and it compresses the other chamber. When the compression is finished, the explosion into the second chamber, and moving this piston into fusion position, back and forth. And then we'll repeat this process again and again. This is actually fabricated micro combustion engine. And this is our coin, very small size. And this is all glass, therefore it's very difficult to see it clearly. And here is a one-shot combustion test, and there's a piston. And when the flame comes up, this piston is moving into the direction. We just record this experiment by using high-speed camera, and within 0.15 seconds, the piston moved to about 8 millimeters. And this one shows the actual beer clip of this combustion engine. It's very difficult to see it, but when you take a look carefully, this is the white one at the center here. That's the piston. It's moving back and forth. Okay, this is all that I have, and I'd like to acknowledge all my graduate students in our laboratory, and we appreciate the financial support from the Ministry of Science and Technology through National Research Laboratory Program, and my collaborators in Department of Chemistry, Professor Kwang, and Department of Biology, Professor Lee, and Mechanical Department, Professor Kwang and KAIST. Thank you.